No. Let's go on 1, 2, 3, go.
I think it's gonna be a little lame though.
No, don't worry, we'll make it work.
Alright, let's do this then. 1, 2, 3, go.
Yeah.
Lame?
Yeah, that was pretty lame.
Alright. Sarah, what are you doing? I'm trying to mark Sarah, I'm trying to mark my test for the past 3
Enjoy
hours.
the
I'm
music.
playing music right now. I can't concentrate if you're playing music. Sarah, that's enough.
Come on! Enjoy the music,
Sarah,
Kari!
I'm going to enjoy the music after I'm done finishing marking my test.
That's such
Right
time.
now.
Guys, I have an idea.
What's your idea, Mike?
Let's just create a noise canceling system.
A noise cancelling system?
Wait, that's a good idea!
Yeah. So you guys are familiar with the basic structure of a sound wave, right?
Yeah.
Peaks, troughs, amplitude, wavelength, frequency. Now, let's say we have a radio here that's emitting a sound at a certain frequency, and we introduce another radio that's emitting the exact same frequency, has the same amplitude, same wavelength, same everything. What do you think's gonna happen, Sarah?
Oh, constructive interference.
Yeah, exactly.
Oh, remember this concept. It caused some grief on my PHYS 1A03 class.
So basically, constructive interference is when you add together two wavelengths. If this has an amplitude of 1 and this has an amplitude of 1 and they're in phase, meaning that the peaks and the troughs line up, when you add them together, they're going to have an amplitude of 2, meaning that the sound amplifies and becomes louder. So let's say we shift this sound wave half a wavelength. What do you guys think is going to happen?
Well, in this case, destructive interference is going to happen.
Exactly. So let's see how that would look. So if we shift it from here to here, that's about half a wavelength. We're going to... So now this whole system has shifted. So what would this be now?
That's a peak.
Yeah. And this is
The trough.
exactly. So where we have a peak in our new system, we have a trough in the first system. Where we have a trough in the second system, we have a peak in the first one. So what's going to happen to these two sound waves?
They should cancel each other.
Exactly, because if we add a peak and a trough, it's going to be 0. Essentially, what's happening here is that air needs to oscillate for sound to occur. So when the first radio is pushing air forward, the second radio at the same time is pushing it backwards. So because they're equal and opposite forces, it's causing air not to move at all, which results in a straight line. Now, if we have a straight line, is sound going to come out?
No.
Exactly. So how do you think we can do this in real life so we can block out Sarah's frequencies?
So Kari can just play the same frequency as me.
Exactly, but how are we going to prevent it from being in phase?
Well, we're going to have to calculate the distance that is required in order to shift the wavelength, so then the two will cancel out each other.
So we know this distance represents half a wavelength. So if we just solve for the wavelength, we should be able to find the distance the two sounds need to be apart from each other.
Sarah, what do you think roughly was the frequency that your music was playing at?
I think it was about 570 hertz.
Yeah, that
Okay,
makes sense.
well, let's shut that down.
And now we know that the speed of sound in air is 343 meters per second if the temperature is 20 degrees Celsius, which this room is. So we can just plug all of that information into this equation.
0.6017 meters.
Yeah, exactly. All right, but earlier we said we needed to shift it half a wavelength, right? So if we divide that by 2, we get about 30 centimeters.
Which is about a ruler.
Yeah, it's about a ruler, so that's how much we need to move it by.
All right, what do you say, Mike, Sarah? Why don't we just run an experiment and see if that actually works?
That sounds like a great idea. Let's do it.
Let's do it.
Basically, how we're going to set up this experiment is we're going to have two frequencies playing on two phones. They're the same frequency, 570 hertz each. And once they're playing at the same time, we're going to shift one about 30 centimeters back. So that's going to represent about half a wavelength. When this happens, the sound waves should be out of phase, which means that destructive interference is going to occur and they're going to cancel each other out. See, I told you destructive interference would work.
I know, listen to this piece in quiet. I guess it worked.